So this is an interesting little exercise that's used to demonstrate how to determine the potential difference between 2 points or two nodes. And so in this case, they're asking us to find VAG. So A is this point and G is here. And so to do this, we need to calculate the voltages for different steps in between there. And then when we add those up, that will give us that voltage or potential difference. So here, the most direct path that we see to get there would be this path here. And so when we look at that, we see that it's a combination of different points. So, if we go from A to B, so then that'll be VAB, and then from B to C, that'll be VBC, and then of course we just keep going along, CD, and then plus VDE, and then plus VEF, and then finally VFG, and that will all equal to what we're looking for. It gets us from A to G, so that's VAG. So now we need to determine what these potential differences are. So we can see right away, we already know this leg and this leg, as there's voltage sources there. So we could just plug those in directly. So now we need to determine what the others are. So let's do that. So first, we want to find VAB. So to do that, we need to find the voltage drop across that. Well, we can do that by realizing that we have a closed loop here, and so we should have a current flowing here. So we'll call this I1. So to determine I1, we just use Ohm's law, which says that that's the voltage over the resistance here, right? And so to get that, the only voltage we see is this voltage source, 24 volts. And then we have 3 resistors, 2, 1, and 5. So it'll be 2 plus 1 plus 5. And so that's 24 over 8. And so that would give us 3 amps. So now we have 3 amps flowing, so that means there's 3 amps flowing through this resistor. So therefore, we can determine that VAB, again by Ohm's law, is just the current and the resistance. And so that will be 3 amps. 3 amps times 5 ohms, and that equals to 15 volts. So that's VAB. So that means then that we have VAB. We said we already have VCD and VFG because the latter two are just voltage sources in between those. So next, we want to take a look at this one here, this leg here. So being that we have a closed loop here, a closed loop here and a closed loop here, there should be no current flow along this branch. So that means the current flow along here, I2, is going to be 0. So then for VBC, if we do, again, Ohm's law, we'll have 0 times 40, which of course will give us 0 volts. So there's 0 volts across VBC. So now we've determined this one. We know VCD, we said that's a voltage source. So now we want to look at this leg here. So if we look at that leg there, again, we are going to need to determine what this current is, but we already know what this current is because we have a current source. And so all that current must travel through that loop because it has to circle around. So that being the case, we know the resistance, we know the current. So then VDE should be equal to 5 amps times 4 ohms. And so that should give us 20 volts. Now we need to take into account the direction that we're traveling is this way, and that current is flowing back against us. So this will be a negative 20 volts. Negative 20 volts. Okay. So that being the case, we now know this guy, VDE. And so now the final leg that we need is this one here. And so when we look at that one, again, we already know the current, we know the resistance. And so VEF then will be equal to the current, again, which is 5 amps, times the resistance, which is 6 ohms. And so we get that will be 30 volts. And again, we're calculating voltage this way along our path, but our current is flowing this way. So therefore, it will be, again, a negative value. Okay? Okay, and so just to make sure we notate this, we said VCD, which we already knew, it just has a voltage source here, which is right here. And we see that it is negative. We hit the negative sign first, so it's a negative 50 volts. And then finally, here, VFG, we have 30 volts. So VFG, and we hit the plus sign first, so that's a 30 volts. So now we should be able to finish our calculation, right? So we know that we have VAG, which is what we're looking for, should be equal to VAB. I'm just rewriting this equation from up top, plus VBC plus VCD. So VCD plus VDE plus VEF plus VFG. So as we plug these numbers in, we have VAB, we said was 15 volts. And then VBC, we said was 0 volts. VCD, VCD, we said was minus 50 volts. So minus 50. VDE, we said was minus 20 volts. VEF, we said was minus 30 volts. And then finally, VFG, we said was plus 30 volts. So now, if we add all these together, what we should have left is a negative 55 volts. So this is the answer. So if I were to put a voltmeter, one terminal at A and one terminal or one lead at G, I should measure negative 55 volts.